So our last topic in probability is Bayes' formula. So this is a formula, something that's called Bayes' rule, invented by Thomas Bayes. He was a fellow who lived in the 1700s. And this formula is really important for really many areas of science. And in computer science, it's especially important in the field of data science and machine learning. So we're not going to see examples of that, of machine learning and data science in this class, but you will see this formula again if you take classes in data science. So we start off with, suppose we have a situation like this, right? So here we have a sample space S, and it's divided up into two parts, S1 and S2. It doesn't have to be exactly in half. The point is there are two parts of the sample space, and then we have an event, right? So we have an event E, which is a subset of the sample space. And as we see in the diagram, it's possible that E overlaps with S1 and overlaps with S2 as well, right? I mean, it's technically possible that E is only in S1 or only in S2, but we allow for the possibility that E is part of S1 and part of S2. Right, that it overlaps with S1 and overlaps with S2. So what we have here is this lighter gray area is the intersection of S2 and E, right? S2 intersected with E. So it's part of E, but it's the S2 part of E. It's the part of E that's also in S2. And then the darker shade of gray is S1 intersected with E. So this is the place where E overlaps with S1. Okay, so this is our situation. And what we want to know is, what is the probability of S1 given E? So in other words, suppose we know that the event occurred, right? So this is different from the types of things we were doing until now. Till now, we were asking, what is the probability of E, right? But here, it's something different. Here, we know E occurred. And now the question is, what's the probability that S1 occurred, right? It's possible that S2 occurred and not S1, right? It's possible that when E happened, we were in S2. So we don't know. So we want to know, what's the probability of S1 given that we know E? We know that E occurred. Okay, so that is our question. And we're going to use Bayes' formula to figure that out. How do we come up with Bayes' formula? So here I will show the steps. So first of all, probability of S1 given E is equal to probability of S1 intersected with E divided by probability of E. And this is correct because we've had a formula that we've seen a formula that in general probability of A given B is equal to probability of A intersected with B divided by probability of B. So we're just replacing A and B with S1 and E, and that's exactly what we have. Okay, next we go a step further and we say that this is equal to probability of S1 times probability of E given S1, all divided by probability of E. So where does this come from? So the probability of E stayed the same, okay? But what we did was we took this probability of S1 intersected with E and changed it into this. And what was our justification for that? Well, our justification was that we've seen a formula that probability of A intersected with B is equal to probability of A times probability of B given A. Okay, so that is what we have here. Now we go a step further, and we notice, well, I wouldn't say this would be easy to come up with, but it is true, it's a true fact that E is equal to this part union this part, right? This darker gray union this lighter gray area. So the darker gray is S1 intersected with E, and the lighter gray is S2 intersected with E. And if we take those two things and take their union, we have E is equal to this. So in other words, instead of saying probability of E, we'll say probability of this, which is equal to E. Okay, so the probability of S1 intersected with E union S2 intersected with E. So we want to know what's the probability of that thing. Now, the thing to notice here is that we have probability of union, And here, S1 intersected with E and S2 intersected with E. These are two. There's no overlap between them, right? These are mutually exclusive events, right? Because there's no overlap between S1 and S2. So if S1 intersected with E cannot overlap with S2 intersected with E. So based on that, we can use the formula. Well, we can say that this equals probability of S1 intersected with E plus probability of S2 intersected with E, right? So this is probability. We need the probability of the union, but since the two parts of the union are mutually exclusive, we can just break them up with addition. Okay, so we have probability of S1 intersected with E plus probability of S2 intersected with E. And now the nothing changed here in the numerator. And now we go one step further and we modify these. We transform the denominator. So using the same formula from before, right? So using this formula from before. So this leaves us with the entire thing we're left with is probability of S1 times probability of E given S1, all divided by probability of S1 times probability of E given S1 plus probability of S2 times probability of E given S2. So this here is Bayes' formula, right? So probability of S1 given E is this. That is Bayes' formula. Now it looks scary, but it's not so strange. I mean, so what we have here is this thing, which is repeated here, right? Which is repeated here exactly, plus the same thing for S2. Okay, so let's just state Bayes' formula. So suppose that a sample space S for an experiment. Okay, so this is a sample space. Suppose S is a union. S equals S1 union S2. All right, so in other words, S can be written as a union S1 union S2, where we know that S1 intersected with S2 is the empty set, meaning there is no overlap between S1 and S2. All right, so that's like this picture here. S1 can be divided up into S1 and S2. Sorry, S can be divided up into S1 and S2, and there's no overlap between S1 and S2. Then, also suppose also that E, which is a subset of S, is an event, right? So E is an event. Then Bayes' formula says the probability of S1 given E is equal to this. And also probability of S2 given E, it's just the same formula, just with S2, is this. So the only difference is in the numerator. Now here is a generalization of Bayes' formula, which is actually very helpful in many data science applications. But we're not going to actually use this generalization, but it's a nice thing to just see for once. So in other words, this is a generalization where S is divided up into multiple little parts, right? So suppose that we have a sample space S, and S is equal to S1 union S2 union ... all the way through union S sub n. So there are S sub n little parts that S can be broken up into, right? So I'm sorry, there are n little parts that we can break S into, right? So we have a big set S and we can break it up into n little parts, where Si intersected with Sj is equal to the empty set whenever I is not equal to j, meaning if I take any random two of these things here, like S2 and S4 or whatever, if I take any two random things, there's never going to be overlap, right? So suppose we have this situation like this, where S can be broken up into n little parts, where there is no overlap among any of those little parts. Suppose also that E, which is a subset of S, is an event. Okay, so E is an event. So here again, then for any Si, for any S sub I, so this could be any, this could be S sub 15, whatever it is, probability, if we want to know probability of Si given E, so if we know the event occurred and we would like to know probability of Si, this is equal to probability of Si times probability of E given Si divided by this long sum, right? So probability of S1 times probability of E given S1 plus probability of S2 times probability of E given S2 plus ... all the way through plus probability of S sub n times probability of E given S sub n. So this is a generalization of Bayes' formula, but all the examples we're going to do with Bayes' formula will involve only breaking up S into two parts, S1 and S2. So, but this is just a nice generalization to see. And I haven't proven this generalization, but it's nice to see anyways. Okay, so here's a actual example that uses Bayes' formula. So suppose so we have two boxes here, right? We have box 1 and box 2. Notice each box has some balls in them, but so box 1 has 3 black balls, 1 white ball. Box 2 has 2 black balls and 3 white balls. So suppose someone chooses a box at random and then randomly takes a ball from it. The ball, now we know suppose we know that the ball is white. So in other words, normally you might ask, what's the probability that the ball is white? Right, but that's not the question here. The thing here, we know the ball is white. What the question here is, what's the probability that the ball is from box 1? Right, so suppose someone behind our back goes, we don't look, and someone chooses the box randomly takes a ball, and then shows us the ball and tells us, here's the ball, it's white. Okay. But we don't know which box they took it from. So what's the probability that the ball is from box 1? So for this, we use Bayes' formula. So in other words, we know the event that occurred. We know that the ball was white. The question is, was it from box 1 or box 2? So what we can do is set up the following situation, or the following sample space. So this entire thing is S, right? This is our sample space. There are 4 possible events, right? One event is that the person randomly chose box 1 and then picked a black ball from box 1. Well, sorry, this is actually not. They're actually, well, yeah, this. Let's say this is a sample space. Yeah, this is a sample space. Sorry. Let me try that again. So again, maybe the person randomly chose box 1 and took out a black ball. Maybe the person randomly chose box 2 and took out a black ball. Or perhaps maybe the person randomly chose box 1 and took out a white ball, and perhaps the person randomly chose box 2 and took out a white ball. So those are our 4 possibilities. Now we'll say S1 is the left side, which is where the person chose from box 1, right? So this is 1B or 1W, but they're both from box 1. So that's going to be S1. It's going to be the left side. S2 is the right side. That will be the case where the person chose from the second box, right? So we have 2B or 2W. And now here we have an event E. The event E, we know if E happened, right? We know that the person picked a white ball, but we don't know whether it was from box 1 or box 2. So this is either 1W or 2W. We want to know what's the probability that the ball is from box 1. So what's the probability of S1? So what we want to know is probability of S1 given E. We know E occurred. Question is, what's the probability of S1? Again, S1 means the ball came from the first box. E means the ball was white. Okay, so here we just use Bayes' formula. So now we have to plug in the appropriate values. So what is probability of S1? In other words, what's the probability that the person randomly chooses box 1? Well, it's random. There are 2 boxes. It's totally random. So it's 50%, right? 1/2 is the probability, right? So the probability of S1 is 1/2. Now we need to multiply that by probability of E given S1. So if we know that S1 occurred, okay, so if we know that the person chose box 1, suppose we know that the person chose box 1. We don't really know that, but suppose we know that the person chose box 1. What's the probability that the ball was white? Well, box 1 has only 1 white ball out of a total of 4. So the probability that the ball was white is 1/4. Right, so probability of E given S1, that's 1/4. Next, probability of S1, we figured that out. That's 1/2. Probability of E given S1, we already figured that out. That's 1/4. Now we need to add probability of S2. So what would that be? Probability of S2 is, what's the probability that the person picked the second box? Well, it's again 1/2. And then we need to find what's the probability that the ball was white, given that the person chose the second box. So the second box has 3 white balls out of a total of 5. So this will be 3/5. If we simplify all this, we get 15/17, which is approximately 29.4%. Okay, so that's the probability that the ball, that if we know if this is a probability where we know the ball is white, this is the probability that the ball is from box 1. Okay, here's another example using Bayes' formula. This is a really classic example. You'll see this in lots of places. So suppose a certain disease occurs in only 1% of the population right now, right? So this does. So what I mean here, what I mean by right now is that, maybe much more than 1% of the population gets this disease over a period of a year or over their lifetime, right? But what we care about is right now. Right now, at this moment, what percentage of the population has this disease? So suppose it's 1%. So now a pharmaceutical company develops a test for this disease. Okay, they make the following claims about their test's accuracy in the event a subject is tested. So they say as follows. In other words, if you take our test, here is what we claim, and we're going to actually take them at their word. We're going to say that the company is not, fudging the data and whatever. They're saying the truth. So they make the following claims. If you have the disease, then there's a 99% chance you will test positive. Okay, good. So it seems pretty good, right? It seems pretty accurate. They also say if you don't have the disease, there is a 99% chance you will test negative. Also seems pretty good, right? Okay, so now suppose you take the test and test positive, right? The test comes back positive. Assuming that the pharmaceutical company's claims are accurate, we're going to assume they are correct. Question is, what is the chance that you actually have the disease? I mean, what's the probability that you really have the disease? Well, you might say, well, of course, it's 99. Well, not really, because they didn't say that if you test positive, there's a 99% chance that you have the disease. Right? Again, they did not say that if you test positive, there's a 99% chance that you had the disease. They did say, however, that if you have the disease, there's a 99% chance you'll test positive. But that's a very different thing. Okay, so we're going to use Bayes' formula to figure out what's the chance that you have the disease. So we set up the following sample space S. So we have 4 possibilities, and I abbreviate them like this. HN means have the disease, but test negative, right? Because in some cases you'll have the disease, but still test negative. Another possibility is that you have the disease and test positive. That's a good thing, right? I mean, presumably, you want to test positive if you have the disease. Anyways, this another possibility is that you don't have the disease, and indeed you test negative. And then there's another possibility. This is a false positive, right? Where you don't have the disease, D meaning don't have the disease, but yet you still test positive, right? So that happens sometimes. Okay, so this is our sample space. These are the 4 different possible outcomes. Now, S1. So now the event here is, well, let's see. S1 is where you have the disease, right? HN and HP, both of them are talking about where you have the disease. Either you test negative or you test positive, but you have the disease. S2 is where you don't have the disease. Okay. And then we have the event E, which is that you test positive, right? But sometimes you test positive and you really have the disease. Sometimes you test positive and you don't have the disease. Now we know that E occurred, right? We took the test and the test came back positive. So E occurred. We would like to know what's the probability of S1, given that E occurred. In other words, what's the probability that I really have the disease? Because it's possible that I tested positive, but I don't have the disease, and that's still part of E. So I don't know which part of E I'm in. So what's the probability that I am in this part of E, where I tested positive and I in fact have the disease? Okay, so we're going to use Bayes' formula. So probability of S1 given E. So again, S1 is the event where S1, yeah, S1 is the event where I have the disease. E is the event where I tested positive. So probability of S1 given E. So Bayes' formula is this. Now let's do it step by step. So what's the probability of S1? What's the probability of S1? Probability of S1 again. S1 means that that I have the disease. Well, the disease occurs in 1% of the population at any given time. So, or right now, the 1% of the population has the disease. So our total, if it's a totally random thing, I don't know anything else, probability of S1, meaning probability of S1, meaning I don't have any other information. What's the probability I have the disease? 1%, right? Meaning 1 out of 100. So that's 1 out of 100. Okay. Now, what's the probability of E given S1? So again, if I know that I have the disease, what's the probability that I test positive? Well, the company told us if you have the disease, there is a 99% chance you will test positive, and we're taking them at their word. So what they're telling us is that probability of E given S1 is 99%. Right? Again, probability of E, probability I will test positive, given that I have the disease, is 99 out of 100. Now we need to divide this by probability of S1 times probability of E given S1, which we already know what that is. That's this. Now we need to add probability of S2. So what's the probability of S2? S2 is the event where I don't have the disease. Well, if the disease occurs in 1% of the population, then there's a 99% chance I don't have the disease. Right? Again, probability of S1 is where I don't have, we're assuming I don't have any other information. Now I actually tested positive. So, but probability of S2 is just simply saying without adding any other pieces of information. Just if I just want to know probability of S2, totally random. I don't have any additional information. I don't know I tested positive. Just general. What's probability of S2? Is 99 out of 100, right? Because 99 out of 100 people do not have the disease currently. So that's probability of S2 times probability of E given S2. So what's the probability that I will test positive given that I don't have the disease? Well, the company told us if you don't have the disease, there's a 99% chance you will test negative. So I'm sorry. So again, probability of E given S2. Right. So, okay. So if there's a 99% chance you will test negative, that means there's only a 1% chance you will test positive. Right. In this case, again, probability of E given S2 means what's the probability that I will test positive given that I don't have the disease? So there's a 1 in 100 chance that will happen. The company says if you don't have the disease, there's a 99% chance you will test negative. So here I don't have the disease, right? S2, I don't have the disease. What's the probability that I will nevertheless test positive? 1 out of 100. Okay, if we simplify this, this comes out to be 1/2 or 50%. So again, the question was, assuming that so we took the test came back positive. We believe everything the company told us. What's the probability that we actually have the disease? Answer 50%, which is really, kind of shocking. So this is, every statistician, every person who talks about medical statistics and things like that has to know this Bayes rule, has to be very comfortable with it. And so, anyways, this is a really an amazing thing. So let's do a little thought experiment to help maybe explain why this actually makes a little bit of sense. Okay, so let's do the following experiment. So let's say we start off with 10,000 people. Okay, so take 10,000 people, group of 10,000 people, and we test every single one of them, right? So, we don't really, well, you can imagine, let's say you have a campus, college campus, 10,000 people. Everyone has to get tested at the beginning of the semester, let's say, whatever. And we test all 10,000 people. So now we know that we're going to have S1 and S2, meaning there are going to be some people that have the disease, or S1 means that have the disease. S2 means are those people who don't have the disease. So now we know that the disease occurs in 1% of the population at the current time. So that means that 9,900 people are going to actually have the disease. We're not yet talking about testing positive or not. We're just talking about people who actually, I'm sorry, these are the number of people who don't have the disease. I'm sorry. 99% of people don't have the disease. So 9,900 people, that's 99% of 10,000. that's how many will be in S2, meaning this is the number of people who don't have the disease, and there will be 100 people, that's 1% of 10,000, who do have the disease. Now the question is, so we give everyone tests. Now we know that the company told us that, and we're believing the company. The company told us that if you have disease, meaning if you're in S1, there's a 99% chance you will test positive. So that means that 99 out of these 100 people will test positive, right? Okay. So, okay. Now also they told us if you don't have the disease, there's a 99% chance you will test negative. So 99% of these people will test negative. However, 1% of them will test positive, even though they don't have the disease. But what is 1% of 99 of 9,900? It's also 99. So what we have here is this event E. If, again, the event E is where someone tests positive. 99 of the, so there's going to be a total of 198 people who test positive. 99 of them will actually have the disease. 99 of them will actually be not have the disease and yet still test positive. All right, so the point is, because there's only such a small part of the population that has the disease at the moment, it's not, this test is not accurate enough, basically. And it just, so we see that if, in other words, if you take someone from this group E that test positive, there's really no way to know if they, assuming they don't have symptoms or whatever, there's no way to know if they actually have the disease or not, because they could be one of these 99 people or one of these 99 people, and just 50-50. All right, so that's the end of this topic of Bayes' formula, and that's the end of probability for us.